Hello, good evening.
Sorry, I wanted to make I muted and don't know that I stopped. I didn't remove the mute. Immediately you talk, I just remember. Sorry. Yes. We want to start our discussion on chi-square this evening. And it may take us 2 or 3 lectures to finish with chi-square. Now, these are the things we want to learn, different type of chi-square we go through. Pearson chi-square. Though, let's say it were to be workshop now, we also run it, but we don't run anything, but there are some SPSS output of, after analysis of some of them. Because what we have here is already we go through the theoretical aspect. We also usually run with SPSS. I give an example. All these examples we show on the slide, how you can solve them, then how you can go about it if you want to run in SPSS. Here we are going to look at Pearson chi-square, Yates corrected chi-square, likelihood ratio chi-square. Is Daniel, which you are disturbing? Chi-square, Pearson chi-square, Yates corrected chi-square, likelihood ratio chi-square, Fisher exact P. That one is not chi-square, but it's used when chi-square is not valid. Then we have chi-square for trend, chi-square for test of goodness of fit, McNemer chi-square, and McNemer-Bowker chi-square. So before we go into all this, it's good to have some historical aspect, historical interlude. Pearson, Carl Pearson, in London in 1857 and 1936, considered the founder of mathematical statistics. Pearson was considered the founder of mathematical statistics. He developed the chi-square test. He published it in 1900, July 1900. He coined the term standard deviation. We talk about standard deviation when we talk about as a square root of variance. So some of those things, you say you quote me plus or minus standard deviation. The man that coined the word standard deviation is this Pearson. He developed the product moment correlation, the Pearson correlation. He developed it, and now you know who to blame. He was first to describe chi-square. We'll look at it, an overview of standard normal deviation. So why I want to make this overview, we have discussed normal distribution. We talk about standard normal distribution. The standard normal deviation we talk about is the standard deviation, Z-score. We talk about the Z-score, the number of standard deviation away from the mean and observation is. Instead of you quoting the value, for example, now, if you have weight, instead of you to say, this person weighs 68 kg, 72 kg, you already know the mean weight for the population. So you now remove the mean weight from each value and now divide by the standard deviation to know how many standard deviation away from the mean. So that will be Z-score. And that is what you use to plot standard normal distribution that we know. that the area under the distribution is 1, which is 100%, with this. The area is 1, which is 100%, and the standard deviation is 1, the variance is 1. So we discussed extensively under normal distribution when we talk about probability and normal distribution. We say, we talk about the continuous probability distribution. We say normal distribution is number 1. It's the most important distribution in statistics. So now, where I'm discussing you go to this is in these places that Pearson, he manipulated this standard normalization distribution to create chi-square distribution. So you see, so this slide first what remind you of the standard normal distribution. So it is Z-score used to plot the standard normal distribution. How is it each score? Can you say X? You minus the mean from it and divide by the standard deviation, it gives you the Z-score. So instead of you talking, say, maybe if the mean weight, for example, like the example I gave before, if the mean weight is 70 and the standard deviation is 10 for weight, for example, it's just an hypothetical example. Somebody that weighs 70 is the mean value now. So the standard deviation is 0. Because if you minus 70 from 70, which is the mean from that 70, it gives you 0. But if somebody weighs 50, you remove 70 from 50, give you minus 20. Divided by 10, which is the standard deviation, it gives you minus 2. That is the number of standard deviation is minus 2. It means that minus 2, that is 2 to the left of the graph. But if somebody weighs 90, and when you remove 70, which is the mean from 90, give you 20. Divided by 10, which is standard deviation, give you 2, which is plus. It means that 2 to the right side. Can you see now? It means the minus 2, the value is less than the mean. The plus 2 is more than the mean. Both of them are equidistant from the mean. I think I've explained it before. So just for you to remember that this is standard normal distribution. The entire area under the curve is 100% or 1. So you remember the properties of the normal distribution. Property of standard normal distribution. We have Z-score. We have is symmetrical. Mean is 0 and standard deviation is 1. Mean, median, and mode are equal. Those are the issues about standard. So if you look at the way we say the area is 1, so if you divide it to 2 with the line passing through 0, it's bilaterally symmetrical. One half is the mirror image of the other. So that shows that the area to one side is 0.5, which is 50% of it. The other side is 0.5, which is 50% of it. 50 plus 50, 100%. 0.5 plus 0.5 mean 1. This is just a summary of standard normal distribution. So what Pearson did, very intelligent man, is to square the normal distribution. So you square it. You know that in the standard normal distribution, as you can see, toward the left, you are seeing Z minus 1, minus 2, minus 3. You are seeing to the right, plus 2, 3. So if somebody square these values, this minus 3, minus 2, minus 1, 0, 1, 2, 3, what will happen? Negative, we cancel negative. Minus 3 times minus 3, it gives you 9. So when you square now, all the negative will go. Of course, minus 3, when you square it, minus 3 times minus 3 is the same thing as 3 times 3. So when you even the value to the right will coincide with the value to the left. So, in standard normal distribution, we have negative value, we have positive value. Because you have squared it to create chi-square, chi-square will not have negative value again. It will start from 0. It is always skewed to the right. Can you see the shape? So by squaring standard normal distribution, you create chi-square distribution. And that was what Pearson did. So the characteristic of chi-square now distribution is no negative value. Means is equal to the degree of freedom. The standard deviation increases as degree of freedom increases. So the chi-square curve spread out more as the degree of freedom increases. As the degree of freedom becomes very light, the shape becomes more like normal distribution. The shape is not at the value. No, if normal distribution, you know that really standard normal distribution, we have negative side, positive side. But The value will not have negative, but the shape will be like that of normal distribution as the degree of freedom increases. We want to talk much about degree of freedom because we have introduced the concept of the degree of freedom when we're talking about this standard deviation mean, when we're calculating variance and standard deviation. That's just an introduction. For each statistic, it's the same logic, but there's peculiarity in the way you apply that degree of freedom to each statistic. When you are talking of chi-square, it's different from when you are talking of t-test or ANOVA when it comes to the degree of freedom, but it's the same logic. We're going to see it. The properties of chi-square distribution, I've already said, it is non-symmetrical, ranging from 0 to infinity, no negative values. Skew to the right. You can see the shape is flattened to the right. So when we talk about skewness, I have negative skewness or positive skewness. The negative skewness is the skew to the left, skewness to the left. The positive skewness is skewness to the right. But for chi-square, usually skew to the right. Total area under the curve is 1. Any probability density function. The meaning of probability density, I said it when we're talking about normal distribution. When you represent probability by graph, it becomes that is called probability density function. And you know that probability cannot be more than 1. So the area under is usually 100%. Whether you are talking of chi-square or normal distribution or t distribution or f distribution, the area under the graph is equal to 1. It's a family of distribution, different chi-square distribution for each degree of freedom, value of degree of freedom. Because you can have different degree of freedom, so the shape of chi-square for different degree of freedom differ. For each degree of freedom differ. The test utilizes a contingency table to analyze data. We're going to see. Contingency table, you're going to see is just a table when you have row and column, the intercept, row and column. The table that has row cells are arranged in row and column. That's contingency table. And it's very simple. If you call chi-square, is used to test association between two categorical variables. So because of that, the categorical variable, so the number of cells in the contingency table depends on the category of the variable you are dealing with. For example, now, if you are looking at association between sex and level of education, where you have sex that either male or female, level of education is maybe we have 4. No formal education, primary, secondary, tertiary. So you may put the level, you may put the sex at least at the row, and the column is the, what do I call it? The level of education. In that situation now, you're going to have how many cells? 8 cells. So, across, you're going to have 8 cells. How the one will be along the road, the other one will be along the vertical. That's contingency table. So degree of freedom is number of row minus 1 multiplied by number of column minus 1. So when you draw the degree contingency table, the degree of freedom is usually number of row minus 1 multiplied by number of column minus 1. So this is a contingency table. So we also know as cross tabulation or cross tab or two-way table. We have 2 examples here now. It presents the distribution of 2 categorical variables simultaneously with the intersection of categories of the category of the variable appearing in the cells of the table. For example, now, look at the first one, the association between male sex and employment status. So the cells have 2 categories, male or female. The employment status has 2 categories, employed, not employed. So when you put the cells along the row and employment status along the column, it gives you 4 cells. It's the gray area that is number of cells. Those blue area is just the addition, is total. If you look at it now, for male now, 90, 40, give you 130. For female, 95 plus 75, give you 170. If you're looking from employment status perspective, 90 plus 95, those are the people that are employed. That's 185. People that are not employed, 40 plus 75, give you 115. whichever way. Everything, the grand total will be 300. So if you had 185 plus 115, give you 300. If you had 130 plus 170, give you 300. That's the way the contingency work. Look at this one for level of education and socioeconomic status. The same thing. So categories of one variable appear in the row, and the category for the other variable appear in column. Each variable must have 2 or more categories. Each cell reflects the total count of cases for a specific category. For example, when you say specific care, look at the first one now. So May that I employ, that's category of May and category of employee. So May that I employ is 19. That's that cell. May that are not employed is 40. Female that I employ, 95. Female that are not employed, 75. The same thing for this other is the same. Now, let's talk more. We still come back to that degree of freedom. Let's now talk about chi-square. There are many. Let's talk more about different type of chi-square now. There are many test statistics that follow chi-square distribution. The one that is often used to test association between two categorical variables is the Pearson's chi-square, because Pearson was the first to describe it, as I've said, Karl Pearson. It assesses whether an association exists between two variables by comparing the observed pattern of value of response in the cell to the pattern value that will be expected if the variable were truly independent of each other. That is, if no hypothesis is true. Remember, when we were in the last lecture, I said that expected value is the same thing as hypothesized value. Hypothesized value. Hypothesized value or expected, it means the same thing. It means what is the value when no hypothesis is true? What is the value when there's no association between the two variables you are talking about? Don't worry, you get to see, practicalize it as you are going on. Different type of chi-square statistic. We have chi-square, Pearson chi-square. That's the commonest one. We used to compare proportion between independent group. We also use it for the goodness of fit test. I explained it last lecture. Goodness, we still talk about when we get to chi-square or test of goodness of fit. So we use Pearson chi-square to compare two proportion or to test measure of goodness of fit. We have likelihood ratio chi-square. It's the same thing. What the person does is what likelihood ratio does. But where the person use division and multiplication, yes, so this one use, when this chi-square use normal division, this one use logarithm. So likelihood ratio use logarithm. So the value initially is a little bigger or smaller than, I think it's bigger. We see example. Bigger, slightly bigger than, just slightly bigger than the corresponding Pearson chi-square. If you solve them with logarithm or solve with Pearson chi-square or normal Pearson chi-square, you get almost the same thing. But people don't usually use that likelihood ratio. People use the Pearson. Then McNemar and McNemar-Bowker, comparison of proportion between peer group. You're going to see it. Peer group, I explained the last time. Peer, when we say peer, when you carry out observation on people, on the same group of people on two occasions, that's peer. For example, now if you determine somebody, if somebody is hypertensive or not by measuring their blood pressure, you say, oh, you're hypertensive, you're not, but you did it for a lot of people. Later, you come back for the same people and reassess it. You know, you may not get the same thing. So some people were classified hypertensive before, they are still classified hypertensive now. Some were classified hypertensive before, they are no more classified as hypertensive. Some were classified not to be hypertensive before, they still remain not hypertensive. While some were classified not to have hypertension before, but they become hypertensive. And you see 4 categories now. It will fit into 2x2 contingency table, but is paired because it's the same people you classify before and after, before you now do your chi-square. So it's different from comparing independent group, because that one is pair group. So when we have only two category of value, like for example, now hypertension, no hypertension, that's McNema. But maybe we have something like maybe socioeconomic class now, upper, middle, lower, three categories that you assess on two occasions. Since the category is more than two, it can be three, can be four or more. You call it McNema Bowker. I think it was the same logic. Bowker now work, build on McNema's work, because McNema is the name of a person that first of all described it. So the person that now describe it further to include more than two categories is Bowker. So they now call that one McNema Bowker. Chi-square for trend, also called concrete amity test for trend. So is a form of chi-square. When you go to see it, when you are trying to look at association between the outcome is two, either yes or no, but the exposure is ordinal. For example, now age group, socioeconomic status, or maybe educational group. Educational group is ordinal, no formal, primary, secondary, tertiary. You know that primary is higher than no formal education, secondary is higher than primary education, tertiary is higher than secondary education. When you say socioeconomic status, you say lower, middle, upper. It's in gradient. Age group, that if you have grouped the age, for example, it's not the age on its own, but maybe you say you group the age, you say less than 20, 20 to 24, 25 to 29, 30 to 34, 35 to like that. You know that it's ordinal already, because you know that the 20 to 24 is higher than less than 20. 25 to 29 is less than 20 to 25. So anything quantitative you have group. If you group into group more than two, it becomes categorical, it becomes ordinal. By grouping is categorical. But when you now have more than two groups for that quantitative variable, it becomes ordinal, because the natural order is there. So we have Mantel-Hansing chi-square. This one is used for stratify analysis. When you want to analyze, you want to break into different categories. It's one group where you want to stratify it. You want to analyze two groups or three groups separately to remove confounder. Yes, the statistic called Mantel-Hansing statistic is a form of chi-square. It follows chi-square distribution. What statistic used for logistic regression? So anytime now we do logistic regression, the statistic you use there is what statistic chi-square. So, but though it depends. Some software like EpiInfo, Stata, so what they present Z distribution as a statistic, because what they actually do is the regression coefficient, which is beta, over standard error. So regression coefficient over standard error follow normal distribution Z. Some software like EpiInfo and Stata, they give it like that. You see Z, which is a normal distribution. But for SPSS, you now square that set. When you square it, it gives you, of course, you already know that chi-square is a square of normal distribution. If they square it, it follows normal distribution. That is what statistic you see in used in SPSS. We have Kruka-Wallis statistic. It is a non-parametric statistic for comparing more than two mean. We are going to look at it. Well, we have time to look at it. So it follows chi-square. We have Laurent statistic. When we use for Kaplan-Meier survival curve, when we talk about survival analysis. So you see, this one you see now is the one I know, I've seen. Chi-square can be, I know that they will even discover many, but a lot of things follow chi-square. That's just the reality. So it's only the one you even know you use. Now, let's talk about requirement. For you to analyze chi-square, two categorical variables must be there. It's for two categorical variables talking on the background. Talking, we need to feel. Please mute. Maybe I have to be muting everybody. Talking. Somebody is disturbing the class. If I give you my pick, this person has no name. Says my pick. He put there is the one disturbing the class. My PC. Yes. So two categorical variables is a requirement. Two or more categories. So for example, to be sincere with you, you cannot run chi-square analysis if one of them has less than two categories. For example, now, maybe you are studying women in antenatal. Sex is not available. So you now put sex. All of them are female. So you cannot sex analyze. You cannot, once you have more than, you don't have, you have only one category of that variable. It's not even a variable anyway. So in one of them, you cannot analyze chi-square. Not talk of even two of them. So you must have at least two or more categories. Two or more categories. For example, now the simplest one you can get is 2 by 2 table. For example of sex and employment status. Sex, there are two categories, male or female. Employment status, there are two categories, employer, non-employer. You cannot get anything less than that. So that is the smallest contingency table, 2 by 2. It gives you 4 cells. Like for the other one, now, if you have two categories and the other one 4 categories, it gives you 8 cells. If it's 2 categories and the other one 3 categories, it gives you 6 cells. Those are conditions. So you must have at least 2 or more categories for each variable. Independent of observation, there's no relationship between itself. What this one just means is that it must be independent, like you have 2 groups, that is 2 different groups, you are comparing proportion between them. The categorical variables are not pair in any way, not but this is just for this one purely for common chi-square person, because we know that McNeman, the categorical variable, have pair, variable are pair. Relatively large sample size. You must have relatively large. If the sample size is too small, the chi-square will not be valid. Expected frequency for each are at least 1. I'm going to explain it. These are, by the time we go into the real something working, so you understand, you appreciate it. Expected frequency should be at least 5 for the majority, 80% of the cell. So when I will explain it further, those are the requirements for doing chi-square. The degree of freedom, the number of independent pieces of information that go into the estimate. Independent piece of information. You the word independent piece of information that go into estimate. I will explain it. But the cram way, the mnemonym, we can call it, the degree of freedom is n minus 1. Then degree of freedom for chi-square will be row minus 1 times column minus 1. You know, the logic behind the degree of freedom is something minus 1. I've explained it. When you have observation and the total is fixed, already fixed. So if you had all the value of the observation together, is already fixed. All the elements can vary their value except 1. The degree of freedom is the number of samples size, the sample size minus 1, generally. But when you now have this degree of freedom 2 by 2 contingency table, which you use for chi-square, the number of row minus 1 and the number of column minus 1. So that's why in a chi-square, you cannot actually say it's the sample size that determines the degree of freedom. Unlike for t-test, it's the sample size determining the degree of freedom. But here is the number of cells, number of categories, the number of categories of the variable, of each of the variable. You are dealing with number of categories of the value. For example, sex, there are 2 categories, male or female. Employment status, maybe just say 1, 2 or so, employer, non-employer. Maybe for education, we say is maybe level of education, we can agree to 4, which are used, no formal, primary, secondary, tertiary. And many like that. Socioeconomic status, maybe 3. We say that low, middle, upper. So the number of category for minus along the row, minus 1. Number of category of this the variable along the column, minus 1. You multiply it, that's what gives it the figure. Let's look at it practically. Look at the example you gave about male, female, employer, non-employer. So the number of independent entry, only one, there's only one independent entry. It doesn't have to be A. It can be the B, it can be C, it can be D, but it has to be 1, only 1. We just use A here. The logic behind it is that, look at the example. We have the grand total to be 300. The total male here is 130. the total female 170, the total employed 185, the total unemployed 115. All these total now, they are not part of the cells. They are just the total. The green aspect in the middle are the cell, 90, 40, 95, 75. 90 mean male employed, 40 mean male non-employed, 95 mean female employed, 75 mean female non-employed. Now, if assume that all the totals are fixed the way they are fixed, if the middle spaces are empty, the green area, all the 4 cells are empty, you can blindly say, okay, where that's 19, you can say 50. If you put 50, that is the only value that is independent. It can be anyone, anyway, any of the cells. If you put 50 in one of them, automatically, that's the only thing that is independent rather. The rest is already fixed, because if you put 50 in one, for example, where 90 is now, you put 50, you know the total along the row is 130. Automatically, where 40 is will be 80. So where female 95 is will be, because the total there is 185, it will turn to 135. So look at it now. When they put 90, let's say where the male and employee, where 90 is, immediately you put 90. Automatically, because the total along the row is 130, so automatically it's 40 that is the other one. Because the total along the column is 185, automatically that one is 95. But when you know 95, you know 75. Even when you know 40, you know 75. Can you see now? It's only one. So you can vary there. That's why the degree of freedom is 1. The rest, you cannot, since the total is fixed now, you cannot say you change that 90 to 110, you want to change another one, it's not possible. You cannot determine the other one. It's already fixed. That's the logic behind it. The number of independent entry is for this degree of freedom, for this 2x2 table, 4 cells, it's only 1 degree of freedom. So if you now use the formula row minus 1 times column minus 1, number of rows is 2. 2 minus 1 is 1. Number of column is 2. 2 minus 1 is 1. 1 times 1, 1. That's the mnemonics, the formula. So it's not the formula per se, is they just find the formula. But the issue is that the real life situation is what I just explained. Only 1 independent entry. That's the degree of freedom of 1. In the degree of freedom of 2, there are 2 scenarios here now that can give you the degree of freedom of 2. You know, for the degree of freedom of 1, it's only 1 scenario, 2x2 table, 4 cells. That's only 1 scenario. For 2 degree of freedom, there are 2 scenarios. You can have 3 row, 2 column, or 2 row, 3 column. So it doesn't change anything. Can you see now? So you see the same thing, but in different 2 ways that it can present itself. So 2 row, 2 column, 3 column, or 3 row, 2 column. Now, you see that the degree of freedom is 2. Because for you, if the periphery, we already know that the periphery are fixed in total. So if you, where A is now, the first one, if you know, you put the value there. You may be able to know the value of B, no problem. But you cannot know the value of what is in C and E and D and F. You cannot know. But until you are able to put in two sets, when you put in 2 sets, then automatically, once you put in A, you know B, C, you know D. C, you put C, you know E. And once you know E or D, you know F. And you see now? So it's the same thing. So it's only, and if you want to use the formula also, look at it. Number of row minus 1. The first one, 3 row, 3 minus 1, 2. The 2 column, 2 minus 1, 1. 2 times 1, 2. This one that is the same thing, number of row, 2. 2 minus 1, 1. Number of column, 3 minus 1, 2. 1 times 2, 2. Can you see now? Now, let's move to the degree of freedom of 3. There are 2 scenarios also that can give you this. One of them, you can have 2 row, 4 column. Or you can have 4 row, 2 column, just like the way 2 and 3. That's the way it comes. And from look at it now, the degree of freedom is 3. Because you can only, for you can have to know up to 3 cells independently before you can calculate the rest can come in. You cannot determine the rest because automatically the rest will fit in. So if you use the same formula also, 2 minus 1, 1, 4 minus 1, 3, 1 times 3, or 3 times 1, it gives you 3. The degree of freedom of 4, there are 3 scenarios that can give you. You can have 3 row, 3 column, or you can have 5 row, 2 column, or you can have 2 row, 5 column. You can see. Look at the one that is 3, 5 row, 2 column, 2 row, 5 column, the same thing, just start change. But this one is unique, 3 row, 3 column. All of them, they have the degree of freedom of 4. And you see now, if you use the formula also, it's the same thing. This one now, 9 sets, 3 minus 1, 2. The other 3 minus 1, 2 times 2, 4. This one, 5 minus 1, 4. 2 minus 1, 1. 4 times 1, 4. This one, 2 minus 1, 1. 5 minus 1, 4. 1 times 4, 4. For the degree of freedom of 5, there are only 2 scenarios. 2 row, 6 column. Or 6 row, 2 column. So the same thing. Those number, the degree of freedom is 5. And you can, if you say 2 minus 1 times 6 minus 1, that's 1 times 5, give you 5. The degree of freedom of 6, there are 4 scenarios. You can have 4 row, 3 column, or 3 row, 4 column, or 2 row, 7 column, or 7 row, 2 column. All of them will give you the degree of freedom of 6. So I think we stop there. Most of the time when you are analyzing, hardly do you have too many. Even if you have too many of them, we usually collapse it because when it's too, especially if the sample size is not too big, so we usually collapse it better. In a situation where you have large sample size, you may be able to accumulate many cells. You still have reasonable result from it. So before we go further, let's look at the shape of, we have already said, apart from the fact that different statistics follow normal distribution, followed chi-square distribution, as I've said, different type of Pearson, likelihood ratio, Monte-Hessing, word statistic, Kuka-Wallis, different, more. There are many of them. I mean, they have not even discovered. But we also said that the chi-square distribution on a graph is a family of distribution. That family has nothing to do with the type of distribution that follow normal distribution. It has to do with the degree of freedom. So the shape of the chi-square depends on the degree of freedom. Look at this one. You see this first graph now, the upper right, the left. You see the degree of freedom on 1, that red one. You see the shape? The degree of freedom on 2, can you see the shape? The degree of freedom on 3, 4. As the degree of freedom increases, it begins to behave like the shape begin to reflect that of normal distribution. The skewness begin to reduce small. So look at this second graph. The degree of freedom of 5, you see the degree of freedom of 10, degree of freedom of 15. Can you see the shape? Look at this one, the degree of freedom of 1, 3, 15, 31. Can you see? So the shape of the graph depends on the degree of freedom. So then what do we mean by critical value? If you remember the other time when we talk about normal distribution, please, I don't want noise. Somebody is making noise. So like when I talk about standard normal distribution, you remember we talk about 95% confidence interval. We talk about the middle 95 for two-way test, the two-tail test. When in that graph of normal distribution, when you carve out the middle 95, the remaining 5% distributed equally on both sides, 2.5, 2.5. But if it is one side, 95, the remaining 5% is on one side. But for chi-square, usually the graph, either you are doing two-tail tests or not, the chi-square is skewed because of the skewness. So you cannot, it doesn't make sense to talk of middle 95, where how will you, the rest, how will you know how the 5 are distributed? So we always talk about one side, 95. So 95% on one side, the remaining 5% on one side. And you know, we told you that that level of significance, that the probability, probability, the total area on the graph is the one that shows the probability 100%, 1. So that particular point where 95 separate from 5, that is the level you say, level of significance usually set 0.05. That is 1 out of 20. So at what, if you are moving from a 0, moving along the lane horizontally, at what point value of chi-square correspond with area 95 on that side and 5%, remaining 5% on it, at what value? That is what we call critical value. Because it's the when you calculate your chi-square, if it has not reached, I've already told you the logic behind hypothesis test. At the value, it starts to do with division. Once the value is greater than 1, then it will reach a critical value that we cannot say this thing, it cannot be that by due to chance, because you have divided the variability by inherent variability. So you expect, because you expect for you to say that this variability, this difference is significant. The difference you are looking for is the one that is numerator. It should be big enough to offset the standard error, which is the inherent variability. It's not only that it will be greater than 1, it will reach a critical point when we say, oh, this one is big. That critical point, as told you, usually corresponds with the probability p-value of 0.05, because that's what usually use, p-value of 0.05. So this graph is just showing it. So if you say the area under the graph is 100 and the probability is 1, so that value of chi-square that move from 0 to a point where the remaining area is 5%, that is a critical value. And that value depends on the shape of the graph. And you know that the shape of the graph depends on the degree of freedom. So, for example, now, for the degree of freedom of 1, that is the one on the upper right side, the degree of freedom of 1, the critical value of chi-square is 3.84. So that was separate 95% of the area and the 5% of the area on this small area. For the degree of freedom of 6, the one lower, can you see? The value is 12.23. That's the way the degree of freedom logic work. How do you use it to calculate, to know when you have reached critical value? Though this one is just useful for calculation for people writing the exam. We explain it to our students, undergraduate, MPH students. Oh, somebody is echoing me. Adija. So, but no, it's just for you to know the logic. So now that the computer does everything for you, you don't need to crack your brain. When you do your chi-square, you see the value. The computer will bring the p-value for you. Because with hand, you cannot know the p-value. We can only know that, oh, the p-value will be greater than 0.05 or less than 0.05 based on the critical value, based on the value you are calculated. Because that critical value is just a benchmark. So when you calculate it may be less, it may be more. It's just for you to know. If it is more than critical, that shows that your p-value will be less than 0.05. If it's less than the critical value, that shows your p-value will be greater than 0.05. Then the computer now will give it to you. Give the chi-square, give you the p-value. So you don't need to crack your brain. So this is just a table repeating what I just shown now. So look at this chi-square statistical table. So you see the area now. When alpha means the level of significance, which corresponds to 0.05. Though it may not be 0.05. It can change, it can be 0.01 you set. But that's why they just put the alpha. But the other one is 1 minus alpha, that is the remaining one. So you see the green area now. is the one that talks about the level of confidence. The blue area is the larger area, which is the green area, is the confidence interval, level of confidence, while the blue area is the significant. And then, I don't know if I've told you, the significant level and confidence level, they are equal to 1. So if your level of confidence is 95%, your level of significance has been set to be 5%, which is 0.01. You know, 95% is 0.95, which is level of confidence. The level of significance will be 5%, 0.05. If your level of confidence is 99%, your level of significance will be 0.01, which is 1%. So this table is just showing. For example, now at the degree of freedom 1, look at it. You look at the degree of freedom 1, and you look at 95% on that green, and which is 0.05% on that blue. You see the critical value is 3.841, which is what I said before. So if you are looking at the degree of freedom of 2, the critical value will be 5.991. Degree of freedom of 3, critical value is 7.815. Degree of freedom of 4, critical value is 9.488. Degree of freedom of 5, the critical value is 11.071. The degree of freedom of 6, the critical value is 12.592, which you saw before. The degree of freedom of 7, the critical value is 40.047. If you have questions, you can be asked. You can. So hypothesis test. How do you test? Just leave this one, because this one will confuse you. This slide will confuse you. I don't want it. So chi-square formula. I don't know what time now, because I don't want to overload people with information, so that this is to 8, 7 minutes to 8. I think we stop here if you have questions. So by Tuesday, we start with this. We now solve our sum. We now look at examples. Example, yes, correction, we will look at it. Look at them. So I think in the next 2 days, we'll be able to finish. Any question? So I've explained the important, can I call it preamble now? Theoretical concept, just to bring you to speed, how chi-square came to be, and some important characteristics. So why I don't want to go further now, we want to have specific example for each type of chi-square. I think it's not good to open it at the end of the lecture. People can be confused. Any question on what we have discussed? Any question? No questions mean that it's simple, straightforward. Is it that it's straightforward? Okay. Let's assume it's straightforward.
Good evening, sir.
Good evening.
Okay, so my question is, you know, when you were telling us about, I think you muted us. Okay, you're telling us about.
No, it's not you. I muted Nunju. So go on.
The contingency table. The contingency table, and you are saying that 1 degree of freedom has 2 degrees of freedom. Do we need to know, like, theoretically, do we need to know, like, how many contingency tables we can get for each degree of freedom? I'm just wondering that. Were you just?
Oh, I'm just you don't need to know. You don't need to know that, or you don't need to know. I'm just telling you the scenarios. It just sometimes when you understand something from back, from it becomes part of you. You know, you don't need to know that.
That's what I want. Well, I just need to know whether it's something we need to, like, memorize for analysis or something.
No, you don't need to know it, but you don't actually need to know. But it just gives you a clue that a particular different type of table may come, and they have the same degree of freedom, or a degree of freedom may be presented in different table, different kind of table. Yeah. Another one? Okay, that shows that the lecture is very straightforward.